think you are all familiar with terms and antecedents and consequence. So this is about fuzzy inference systems, but we need to look deeper whether they are really appropriate for this particular purpose, and if we should really invest time on fuzzifying things which are already a bit fuzzified, so to say. And last part is related to multi-joint preconcept lattices. This is also something we defined as work in progress, but not the topic for today. And when talking about aggregation operators, we started just with research of risk factors and applied numerical values to these risk factors and tried to aggregate them in a simple and common way using aggregation operators. It is not a mandatory requirement to say that the highest risk levels have values close to 1 and the lowest close to 0. It can be inverted. However, there are some hurdles when we do this inversion and when we start working with T norms instead of T conorms. As part of this research, I also tried to combine several aggregation operators because there was an obvious situation that when we started to aggregate values, they started to increase quite rapidly, and then there was a need to slow down this increase a bit. And therefore, there were some other proposals considered. But the fuzzy inference system is a standard way for working with input and output values. And for fuzzy inference system, this is a standard decision-taking process. Therefore, it is a must requirement for our research to consider if it is suitable for this particular purpose and assessing risks, or still there are some setbacks and obstacles in considering mathematical concepts for this purpose. Then, of course, we understand that when constructing membership functions, there are constraints related to specifics for risk assessment process, because when it comes to risk assessment, there are many cases when we see that risk increases sharply and we see that situations that risk is inevitable. Therefore, drawing triangular membership function makes no sense in many cases. We will see later on that there is analysis of using trapezoidal membership functions, but again, these functions are very sharp and close to 1 in many occasions. And then when we consider aggregation, then of course we need to consider how we aggregate these membership values, and fuzzy inference systems are very good for this purpose when we need to understand how we combine, either we take minimum maximum values or product or some other more sophisticated T norms for obtaining the final value. And this is just a brief reminder what is fuzzy inference systems. If you search Google, you can find that there are a lot of illustrations provided as part of MATLAB package, where you can see the pictures describing this process. And this is not straightforward process. Basically, this is at least 2-step process where we take input values, relate them to output values. And these input values can be either crisp or fuzzy. Again, when we consider fuzzy values, there is a certain risk that we apply too much fuzzification. And then we use rules and inference engine to produce fuzzy output values. And the names of Mandani and Sugano, I think they are well known for today's audience. And actually, there are more actions behind the scene. This is what we see on the clear levels that, for instance, fuzzification, we convert crisp inputs into fuzzy values. Then we use quite a lot of rules if then that describe how the inputs relate to the output. And of course, the more variables we have, the more sophisticated rules we need. And it is quite easy to get lost among this set of rules, to be honest. Then we also have this inference engine, for instance, MATLAB package. And the last process, defuzzification, it is not related to direct aggregation, but it is the last step, which is heavily impacted by aggregation that has been done before as part of this fuzzy inference system. If we take the risk severity, we can try to create the membership functions and consider two standard things, for instance, a possibility happening, for instance, the risk assessment that is used in a project management is widely based on uniqueness of certain projects, but also they can take into consideration historic projects and assume that one or other project may fail because many similar projects have failed, and therefore this assessment of failure could be closer to one. But of course, if this is a unique project and if you consider it as a normal and there is no risk of failure, then you can say, okay, there will be risk of possibility of failure close to zero. And monetary impact, that is something that can be characterized using tangible value. Either this is loss from project failure, or in case of financial industry, you know that we often talk about fines. And this is not just about financial industry, it's about each and every person doing business as part of a legal entity, and legal entities are often subject to different fines, not only from financial authorities, but also from consumer protections, competition, and other related authorities. As part of the next step, we introduce these membership functions for assessing risk severity, and this will be important for output part. And then we can grade either risk in some risk scores and interpret these risk scores as very low, low, medium, high, critical, or in the most of the cases, 3 levels are fully sufficient and there is no need to go even deeper. But just to have more colors, we take more values here. And the output value is a risk score. And of course, we can use this risk level matrix. Here we have an example of membership functions. As I mentioned before, it is very tricky to use triangular membership function as one shown for medium risk, because then we have some uncertainty and unclarity what's happening during these areas of intersections where we see that these lines intersect. And then, of course, there is huge dependencies that these intersection regions provide and impact output results and provide output results which are not considered as correct. And as you can see here, I use 0-1 scale for possibility and membership grade 0-1 to characterize what we consider as low, what is medium, and what is high possibility. For financial impact, you can see that picture is already a bit different. And as I mentioned before, it is not very efficient to draw triangular membership function, because here we see that basically these sums could be interpreted in a quite flat way, overlapping somewhere in between 100,000 and 500,000. And everything starting from 600,000 should be considered for high already here. And then the final part for the risk score, as mentioned before, I choose 5 values and use these levels of very low, low, medium, high, critical. And what is next? And I will provide just a visual example how we can write ifs and rules in a quite concise way, putting all the values in one table. Here we see that basically we have a medium on the one diagonal and critical when combining high, high and very low combining low, low. And this can be interpreted using just simple colorful matrix. And for instance, going back to these previous slides where we can see illustration, if we take the possibility equal to 0.65, which is somewhere in the middle, and impact equal to 650,000 euros, either using this table or risk matrix, as we call it in a professional way, then we see that we end up in a situation that we can get the risk score equal to 3.5, which is still high, not critical. The colors are a bit distorted here, but yeah, let them be here this way. This is how it can be visualized, and aggregation works in this first step when we need to consider what's happening on the left-hand side, and definitely we will need to combine maximum T-norm, minimum T-norm product and Kammacher. There are many other T-norms which can be used, but these are just simple examples telling that either we take maximum or minimum, there is still a risk that some of these T-norms do not work for particular purpose related to risk assessment. Why? Because averaging is not very suitable in this context. On the other hand, when we take maximum T-norm, we understand that maximum doesn't consider minimum values. However, when going to minimum values, we need to recall what we use for maximum. If we take maximum of the possibility and minimum on impact, that's the way how these things are combined, and basically that's the main topic of this headline on combination of T-norms and econorms. Just a reminder of simple definitions, and as mentioned before, application of minimum T-econorm results in the aggregated value, which considers the lowest value. There are many models, and you can find them in internet or different publications that confirm that it is quite appropriate. But again, there is something specific behind risk assessment that is on the level of risk being related to incorrect result at the end. And the same applies to maximum T-norm. These are just the two most commonly used T-norms because they are not sophisticated, and you can draw the lines and take the values and get them for further use as part of declassification. I will not devote time to explain what we have under declassification, but we'll have just a brief summary how declassification operators can look like. They are not pure aggregation operators. But under this part, then we see that with product T-norm, product T-norm Kammacher, and it is again very specific related to particular risk assessment model which T-norm or T-econorm should be selected. And one of the last slides, overview of some declassification operators. Here we have them listed as maxima, center of gravity, index, center of gravity, mean of maxima. But At the end, we see that this is already the falsification process where we need to use another concepts. And my main worry is that when going step by step after combining all T norms or T connorms as required, we may end up that the falsification is another bottleneck for obtaining meaningless results for the purpose of risk assessment. And concluding this, we can say that certain stages of the fuzzy inference systems used in risk assessment may cause unnecessary sophistication. That's something I mentioned at the introductory part, where we see that we already have something fuzzified, and if we fuzzify these things further, then we may get lost. Outputs are fully dependent on construction of membership functions. That's what we saw in this practical example. Application of more sophisticated aggregation operators and their combinations may improve the results of outputs, just because that could be better landscape and environment for using this. And enhanced combination of all aggregation operators is subject for future research.
Okay. Most probably it's due to literature you have used, but it's quite strange to use notation S for T norm.
Yeah.
And maximum T norm and so on. So maybe
I have different usage in different slides. Thank you.
So of course we should be careful and try to keep the standard notations.
Okay.
Okay. Some other questions or comments? If not, thank you once more. And the second lecture is a Czechoslovak collaboration. Will be presented by Radek Haláš, and it was called by Jožko Poč from Košice and myself. Radek is from Olomouc. We will, be by the topic of Archimedean T-norms, speak about special form of elliptic variance. Radek, it's your turn. Okay, sorry.
Okay, so as Radko mentioned, this is a joint talk with Jožko Poč and Radko Mesiar. This is about some kind of Archimedean T-norms, which is a small contribution to this theory of Archimedean T-norms. And front is here. Okay. Yes, it seems to work, yes. So here is an outline of my talk. First, I'll give you some ideas about motivation and overview. Second part is about background, basic definitions, and representation of Archimedean T-norms. In the third part, I will recall what 1D and 2D linear splines are, how these concepts are defined. Fourth part is already devoted a key geometric tool which leads to a solution of the problem I will mention. And the fifth and sixth part is about main theorem characterizing spline T-norms which are generated by linear spline generators. So what T-norms and copulas are, I think everybody knows these two notions, T-norms model conjunction in fuzzy logic, and for this serve as aggregation of degrees of truth. Copulas model dependence between random variables. And Archimedean families of T-norms or copulas are very important because they are quite simple, and these are defined by formulas which are easy to handle. Core question I will try to discuss here is an open problem when an Archimedean T-norm or copula is in fact in the form of 2D linear spline, and I will explain how this property relates to their additive generators. So I will recall a basic notion concerning Archimedean T-norms. Every Archimedean T-norm is generated by an additive generator, and it has been proved in a recent paper by Kuchak-Kinayat, Messias Stupnyanova, and me in systems paper about two copulas and linear splines, and that those which are generated by 1D linear spline have to be 2D linear splines. But the converse remained an open problem in this paper. So in my talk, I will deal with proving the converse implication, which says that if an Archimedean T-norm is a 2D linear spline, it has to be generated by 1D linear spline, in fact. And as a geometric tool for this proof serves the property which we call the so-called upper corner condition. Now I will go to details. Here I recall the notion of T-norm, which is commutative, associative, and monotone binary function, which satisfies some boundary conditions. I will not go into details. Every T-norm is between drastic T-norm and minimum T-norm. And in this talk, T-norms which will be considered are always continuous. And continuous T-norm is called Archimedean if we input any element which is different from 0 and 1 to this T-norm, then the result is strictly below this element, which means that repeated conjunction strictly decreases the truth, yes, unless this element is not equal to 0 or 1. And of course, this property excludes idempotency. For example, minimum T-norm is not Archimedean, yes, it's clear. And copulas, of course, the definition is standard. Everybody of you probably know this definition. And Archimedean copulas are those which are associative and satisfy the same condition as Archimedean T norms. Yes. And why copulas are important? There is a famous Clark theorem which says that each multivariate distribution can be decomposed in a way as it is depicted, where C is some copula. Yes, and this copula is unique in case of these marginal distributions are continuous. What is very important for us, that continuous Archimedean T norms can be represented in the form as depicted, where f is continuous strictly decreasing function, f1 equals to 0, and g is so-called pseudo-inverse of f. This is also standard definition, I think, for pseudo-inverse. And this property, yes, another thing is that this generator is unique up to a positive multiplicative constant. That's why we can define f1 to be equal to 0. There is no restriction on this property. From the generator, it can this equality can be rewritten in the following form. So it is a kind of functional equation here. T is an Archimedean T norm, G is its pseudo-inverse, and this equality has to be fulfilled. So T is connected with G also in the following way. It's clear that if T is piecewise linear function, this identity strongly constrains the shape of the pseudo-inverse G, and that G has to be strongly connected with properties of T. Yes, and convexity plays a role that if we have an Archimedean T norm which is too increasing, and then it is a copula if and only if its generator is convex. Yes, so only convexity has to be added to obtain a copula instead of Archimedean T norm. So these are very simple statements. Convexity gives copulas only. Yes. 1D linear splines are continuous functions which are composed of finitely many line segments, and 2D linear splines mean that we have a triangulation of a square, and above each triangle we have a linear surface. That means a plane surface above each triangle, and of course it has to be continuous. Yes, and that means that above each triangle we have a linear form of a corresponding T norm. And it is almost obvious that if the generator is 1D linear spline, then the induced Archimedean T norm is a 2D linear spline, but the converse is not clear. Yes, and the crucial property which gives us a converse direction is the so-called upper corner condition. It simply says that there exists some element smaller than 1, such that in some segment this Archimedean t-norm has a Lukashevich form. So it can be visualized like this, yes. So t-norm has to be Lukashevich in the right upper corner, yes, of a unit square. And what is it good for? Central lemma, which leads to a solution, says that if T satisfies the upper corner condition, there must be some element greater than zero, such that the pseudo-inverse G is linear on the segment between 0 and Z. And consequently, what does it mean that to be planar Lukashevich near the point with coordinates 1, 1 forces linearity near 0, yes, for the generator. And this is the seat of linearity that can be extended, in fact, to the whole interval between 0 and 1. The next key step was to prove that every Archimedean 2D linear spline has to satisfy the upper corner condition. What does it mean? The idea is prove that triangulation gives finitely many planar parts, yes. Boundary conditions heavily constraints how planes look like near the point 1, 1. And associativity prevents arbitrary planes from meeting near the point 1, 1, yes. So forcing the Lukashevich plane in the right upper corner. And from step 1, we proved that the upper corner condition holds. From the equivalence lemma, G has to be linear at some initial segment between 0 and Z. And if we use the functional identity, which gives together a t-norm and generator, we extend linearity on this basic interval between 0 and Z to the full interval 0, 1. So main theorem says that if we have an Archimedean t-norm with an additive generator F and its pseudo-inverse G, then to be a 2D linear spline, it is equivalent with saying that generators F or G have to be both 1D linear splines. So these have to be vice versa linear functions. So we exactly know which t-norms can be parameterized by 1D linear spline generators. These are exactly those which are 2D linear splines. And if we require convexity of the generator, then we obtain Archimedean copulas, in fact. So conclusion, we have shown that there is an equivalence between spline geometry of Archimedean t-norms on the rectangle 0, 1 square and spline geometry of the generator on the unit interval between 0 and 1. And the upper corner condition was the main geometrical tool to prove this. And only convexity determines when the T-norm is a copula. Yes. And of course, it can have some important applications because Archimedean T-norms or copulas are given by generators, and you can simply, by choosing appropriate generator, you will obtain appropriate properties of the corresponding T-norm or copula. So that's practically all. Thank you for your attention.
Thank you, Radek. Some comments or questions? Okay, so the main problem here, of course, was hidden in the fact that if we have a composition of functions, so composition of linear splines is again a linear spline, but this is only, say, sufficient condition. So we can obtain, of course, for any function, you compose it with its inverse and you obtain identity, which is linear spline. So we see that the result being linear spline, this means, for example, copula, that is, or T-norm, that it is two-dimensional spline. It's not so trivial to see what are these additive generators. So now this, say, small problem was somehow solved, that here it is if and only if question.
Yes. Yes.
Of course, it would be interesting to ask, and what higher dimensions? Because there are more restrictive conditions on additive generators. As we have here convexity for additive generator, there we will have something like convexity related to first derivative. And linear splines, of course, imagine that they do not have first derivative up to trivial case of identity. This is Lukashevich in some sense, but its inverse is not linear spline of corresponding situation.
Yeah.
Okay, so unfortunately, this means that we cannot continue with higher dimensions here. Some other questions or comments? If not, thanks. We will go where? So we are going to Iran?
Yes.
Okay. So the next presentation was prepared by Martin Kalina from Bratislava and his PhD student, Fateme. So Fateme, please present.
Thank you.
I am not told that she will speak about divisibility of aggregation functions in the thesis.
Thank you, Professor. Hello, everybody. My name is Fateme Kuchaki-Nejad, and I would like to speak about divisibility of aggregation functions on banded lattices, which is a joint study with Professor Kalina. Doesn't work. Okay, thank you. First of all, I would like to review some known definitions and notations. A bounded lattice is a structure in which for every two elements we have meet and joint, which exists in that lattice, and that lattice has the top and bottom elements 1 and 0 respectively. If all elements are comparable, then we can say that it is a finite chain. And here we just consider bounded lattices, even if we don't mention it. This lattice has a partial order, and 0 and 1 are least and greatest elements of L. If no confusion, we will omit the indices L. So it's the same if we use it or not. Okay, one notation, if we have two elements of L and they are incomparable, then we use, this notation, and we will use this notation for all elements that are incomparable with A. Okay, definition of aggregation function. If we consider L as a bounded lattice and N belong to natural numbers fixed, then A from L will be an n-ary aggregation function whenever it's bounded and it satisfies boundary conditions and it is increasing. Here we just consider binary aggregation functions. An operation on L is called T-norm if it is commutative, associative, increasing, and has a neutral element 1. And if we have a neutral element as 0, then we will call it T-norm. An operation which is commutative, associative, increasing, and has a neutral element E, we'll call uninorm. Also, an operation with the same properties that have annihilator R and satisfy in these two equations, then we call it null norm. And just to know here, we consider proper uninorms and null norms, which means that we don't consider elements 0 and 1 as neutral elements of uninorms and 0 and 1 as annihilator elements of null norms. And if we consider one uninorm U with neutral element E, then this U behave like a T-norm on this interval and like a T-conorm on this interval. These two T-norm and T-conorm will be called underlying functions of the uninorm. The same will be for any null norm. So for any null norms, we call this T-conorm and this T-norm as underlying functions of the null norm N. Okay, now we want to start the main idea of this study. As you know, divisibility is one of the most important properties for operations, especially for aggregation functions. Until now, the divisibility on some T-norms, T-conorms, or for example, some associative aggregation functions have been studied just on the finite chains. So there is no general definition for all aggregation functions which are divisible on bounded lattices. So here we try to define a unified definition for all aggregation functions, and even more because here we consider a star as an operation which is just monotone in right argument. So it is even more general than aggregation function. So this is pointwise divisibility. And from pointwise divisibility, we will reach divisibility. If we have a star as an operation on L, and it is monotone in right arguments, then we say a star is right pointwise divisible at point Y. If for this fixed Y and for all X belong to this interval, then there exists an element which satisfies in this equality. It means that we can somehow characterize and somehow, show and derive one output from two inputs. And similarly, we can consider left pointwise divisible at Y. Again, if we fix Y, then for all X in this interval, there exists one element such that satisfies in this equality. As an example, consider L as this set and A and B between 0 and 1. A and B are incomparable. And this operation. Okay, if we consider just point A, then x will be in this interval. You may remember the interval in the last definition. We computed this interval, so y will be a and x belong to this interval. So for such x, if we consider z equal to x, then we can have the desired equality. So star is left pointwise divisible at a. Similarly, we can prove and show that star also is left pointwise divisible at any y. But if we want to consider right pointwise divisibility, we can see that when we consider point 1, there is no z such that we can have this equality. So this operation is not right divisible at this point. So it's an example of operation which is right divisible, left pointwise divisible in any y, but it is not the case for right divisibility. Okay, we say operation star is pointwise divisible at y if it is pointwise divisible left and right. Also, we call a binary operation right divisible if it is right pointwise divisible at any point of lattice. A binary operation also is called left divisible if it is left pointwise divisible at any element, and it is divisible if it is both right and left divisible. And clearly for commutative operation, left and right divisibility coincide. So from now, if we know that our operation is commutative, then we just consider right divisibility. As an example, if we consider unit interval, and this operation clearly it is monotone and commutative, so we just consider right divisibility. And you can see that if we choose this z for all y, we will have right pointwise divisibility. So it is right pointwise divisible, and therefore it is divisible. Okay. Here we want to tell that, okay, not all operations clearly are divisible. It's it's an example of a non-divisible operation, which is the Tarasic productino. This operation is not divisible on any bounded lattice. Okay, here we want to continue and focus on null norms and uninorms. First of all, we would like to review one definition of some special cases of, or some special group of null norms. So if we have R, S, and T, then this operation is a null norm with annihilator R. And now immediately we have this theorem. If we consider this null norm, then it is divisible if and only if T and S are divisible. But it is just one special case, so we need to prove it for more general null norms. Here we need some notation. This notation will be used for the next theorem to characterize some kind of divisible null norms. This is that theorem. Okay, if we have one null norm and R as its annihilator, then N will be divisible if it fulfills, if these conditions fulfilled. So first of all, underlying functions should be divisible, and with this notation, we should have these three lines. As you can see, this theorem doesn't characterize all divisible null norms. It's just some group of null norms, and it remains as an open problem to characterize all divisible null norms. And as we will mention later, it can be for the further research. One example, we have this L, and this Z is the set of integer numbers, and the order is as this figure. And you can see the elements in Z are incomparable to other elements, just these two. And if we consider null norm by this formula, then we can easily show that from that theorem, this null norm is divisible. Okay, now we want to switch to divisible uninorms. First of all, we would like to say that if L is the bounded chain, there is no divisible uninorm. However, pointwise divisibility can be achieved at some points. So for general, we can't have any divisible uninorm on any bounded chain. And this theorem is for characterization of divisible uninorms. Again, this theorem cannot characterize all divisible uninorms, since, as you can see, we have some conditions here. Usually a uninorm is a neutral element. 0 should be partial annihilator of the elements which are comparable with E, except 1. And also 1 should be partial annihilator of the elements which are comparable with E, except 0. R should be neutral elements annihilator. So we have these conditions. Then with these conditions, we can say that, okay, uninorm U is divisible if and only if the followings are fulfilled. So again, there is no full characterization. And later we will give one example that show one kind of divisible uninorm which does not satisfy these conditions. One example, if we consider L like this and uninorm with this formula, then again, using the last theorem, we can show that if we follow the steps of that theorem, we can say that this U is divisible. And another example for this L and this order and uninorm defined by this formula. Again, we can characterize and say that this uninorm is divisible, and it satisfies the conditions of that theory. Okay, as I told you before, now we want to present one example of a uninorm which doesn't satisfy in that theorem we presented, but still it is divisible. If we consider T as a divisible T norm on L1, S as a divisible T conorm on L2, and L equal to the product of L1 and L2, then uninorm with this formulation will be divisible. And it is an example of uninorm which doesn't satisfy the condition of the given theorem. Okay. Here we propose a unified definition for divisibility of aggregation functions on bounded lattices. And relying on this general setting, we characterize some kind of divisible null norms and divisible uninorms. And as I told you before, it remains as an open problem to characterize all of divisible null norm and uninorms. For further research, one can consider the study of divisibility in border classes of aggregation functions within the lattice-based aggregation theory. And just to shorten the presentation, we omitted some very mathematical and technical theorem, but the main idea was what I explained. And these are some references of this study. Thank you very much for your attention.
Thank you, Fateme. We have time for questions, comments.
Only one question about the relation in the first example. Maybe it was
Yeah.
defined, but first example,
Is it?
yes.
Okay.
A is lower than B. It was defined for
Where?
this relation in the first row.
Okay.
Yes.
This is
Yeah.
diamond lattice.
Oh, it's the diamond lattice.
Yeah.
Okay. Okay.
Thank you, Marta. Some other questions or comments? Okay, Radek.
So
It's a new one.
it's yours. Yeah.
Martin.
My question is, why it is divided into this?
I can confirm they have worked hardly on it. But we have time.
Just a short answer. This is a unified definition that works for divisible T norms and also T norms. Since by now there is one definition for divisible T norms and another for divisible T norms, and nothing that would couple these two definitions.
In some sense, they are the same, but with some difference. But this definition unify all of this definition together, and you can derive those classical definition from this definition.
Of course, not only divisibility, but say smoothness is also involved. And maybe based on Bernard's lecture, it could be interesting to think also on divisibility on other structures like trellises.
Yeah.
But okay, this is already out of this topic. So if there are no other questions and comments, thank you
Thank you
once
very much.
more. His contribution himself, there is Herman as well, which is entitled Relationships between multi-phase structures and unions construction members.
Thank you so much.
Okay. Later we will check it.
Okay. Yeah. If you can. Yeah. I have here. Yeah.
Sure.
Here, right? Okay, but I need to have. Okay. Good afternoon, everyone. Sorry because I take the slide very late. Thank you for the introduction. I'm Ander Roñi Medrano, and I'm going to speak about the work that I have done with my supervisors of the THD, which are Raúl Pérez Fernández and Marisol Gómez. I work in NAIF Center, Naval Artificial Intelligence Research Center, and I am going to speak a little bit about the relationship between the structures of boundary lattices and uninorms construction on that lattices. Okay. Well, Fatima do a very similar introduction, so I'm going to go a little bit fast in this first part to don't say again all the same, okay? But I'm going to introduce the arrays of functions. After that, we are going to see lattices and some properties that we are going to be useful for us. Also, we are defining uninorms on over boundary lattices, and we are going to see some constructions, some particular constructions on some of these boundary lattices. After that, we are going to spell some particular partition that we can do in some lattices and some blocks construction that we work with. Okay. So all of us know an aggregation function is a function for one set to itself, which is not decreasing for every variable, and who satisfy this condition that we can see in the slide. And in particular, we are going to focus on uninorms. Uninorms are commutative, monotone, associative aggregation functions, which have an neutral element within the unit interval. Okay, we can extend that to a lattices, as we can see after, and also uninorms are the extensions or the generalizations of very well-known T-norms and T-conorms, because these are functions satisfying the same properties, but instead of have any neutral element in the unit interval, they have the 1 and the 0, the 1 to T-norms and the 0 to T-conorms. So, as we say already, a lattice is a poset for which every two elements have a mid and a join. In particular, if we are speaking about bonded lattices, we are going to, when the lattices have a bottom element and a top element, usually denoted by 0 and 1 respectively, we speak about bonded lattices. Here we can see a set of a divisor of 12 ordered by the divisibility, in where, in this case, 1 is the bottom element and 12 is the top element. Also, we can see that, for instance, that 2 and 3 are not comparable, since 2 is not the divisor of 3 and 3 is not the divisor of 2. Okay? So, continuing with these no comparable elements, we can define this subset. This subset is a little bit different as Fatima introduced us, because we are speaking about the subset of elements that are in one subset of our lattice. Okay? So when the subset is the same as our lattices, we are going to use the normal notation. Okay? So when we are speaking about lattices, we know that we can take a lot of properties. In particular, I'm going to focus at first in this table's bonded lattices, which are that the subset of incomparable elements of the element E is or empty set or a subset of the of a sublattice or our lattice. Okay. In the case of the lattice of linear sublattice, we are going to denote as 0 star the bottom element and 1 star the top element of the sublattice. Okay. So for this kind of structures, we have different properties that we can see also in the animation that is going to pass the one-to-one. For instance, we have the property A, we told us that there exists an element between 0 and the element E, for which all the elements between the bottom element and this element are comparable with every element of the 0E interval. Analogously, for property B and property A tell us that both are false. I mean, property A and property B. Property A1 tells us that every element of the incomparable elements with the element E, they are the same relationship at 0 star, the same relationship with the mid, with the infimum, and the property B1 is saying the same, but with the interval E1 and the supremum. And again, the property B1 is that both false. And for the property A2 is very similar to property A1, but we are asking to be the infimum of any element of the incomparable element with the element E, and any element of the open interval 0E is the bottom element. Okay? So with all these properties, we are going to see a little bit after how we can define some uninorms, some particular uninorms. But for that, first we are going to introduce uninorms over bonded lattices. It's in the same way that we can do for the neutral element, but for lattices. I mean, it's a commutative, associative, and monotone function with a neutral element within the bonded lattices. Okay, so as Fatim told us, we have this relationship between t-norms, t-conorms, and uninorms. The restriction of uninorms to zero interval is a t-norm. The restriction of uninorm to the E1 interval is a t-conorm, but the new thing appears when we are working with elements that are incomparable with the neutral element. Okay, so some construction that we can find in the literature, for instance, are these two. I take two randomly that are useful to my purpose, but there are a lot. And for example, the first one, it can be applied to every bonded lattices. But in the second one, we have this condition. So to us who say that we need that every element of the incomparable elements with the neutral elements and all the elements in this part of the lattices, they must be incomparable. So this assumption cannot be applied in the first bonded lattices. But the good point of the second bonded lattices, of the second construction is that for the bonded lattices where we can apply it, we have more flexibility of choice. I mean, we have one t-norm and one t-conorm to change instead of have only one, or in other cases that we have zero aggregation functions to change. So continuing with this idea of flexibility of choice, we can find this construction in where the authors take a more restrictive bonded lattices where they were able to apply 3 aggregation functions instead of 2, 1, or 0. Okay. In this case, they take one t-conorm. Also, they have a dual theorem where they apply with a t-norm. So our idea was to continue a little bit more and go a little bit more far. Okay. Here we have how the uninorm work. Okay. But we are going to define one particular partition. To speak about this, I have to recall what complemented elements are and what a partition is. So we say that in lattices that 2 elements are complemented when their bottom element, where their infimum element is the bottom element and their supremum element is the top element. Okay, and a partition is of a set is a family previously disjoint for with non-empty, for which union is the whole set. Okay, so we can do this partition in where we have one lattices, and if there exists 2 lattices, L0, 2 sublattices, L0 and L1, for which every element are complemented, so we can make this kind of partition when we take the bottom element, the top element, and these 2 sublattices. So we are going to speak about partitionable bonded lattices. Okay, we can see here like one bonded lattice, other bonded lattice, all of them complemented with the 0 and the 1, and this is our lattices. Okay, if we are able to do that, then we speak about partitionable bonded lattices. We can extend this idea a little bit more if we can do that every time that we want. Okay, in this recursive way that we can see also in the animation, that we have this kind of partition with a lot of bottom and top elements for each lattices, and we have all the lattices that is complemented with every point of L0, we have a bottom element, a top element, and so on. So for this kind of constructions, we are going to be able to define a nice uninorm construction. Okay, so first, we are going to see how we can define a uninorm which depends on another uninorm. For this, we take an irrepartible bonded lattice, which is, because I think that I don't say that, in this, no, I don't say that. We have here some elements which are comparable with every element of L1, for instance, M1 or M1 minuscula or M1 majuscula. And So we are going to speak about e-portable the same way here with a lot of is and e-portable with a vector, okay? So for this kind of structures, we can define one uninorm, which we have t-norm, t-conorm, which are greater than 0 to every pair of elements greater than 0, smaller than 1 to every pair of elements smaller than 1, and here any uninorm. So this delta is going to be or 0 or 1, depends on the analytic element of the uninorm, and the function A is either or the infimum or the supremum. So we are able to define this kind of uninorm which depend on other uninorm. So if we are able to do that with the first e-particle bounded lattice, if we take an e-particle bounded lattice with being a vector, we are able to define this kind of uninorm. We depend on another uninorms of this kind and depend in another. So we have those recursive uninorms which depend in a lot of uninorms, as we can see here in the slide, where we are applying this big uninorm over all the lattices. Then this is the incomparable elements with the neutral element which is here. So we are applying to this bounded sublattices this one, and so on and so on. So I finish with this slide, and thank you so much for the attention. Mila esker arretagatik.
Thank you, Ander. We have some time for questions, comments. Nobody? So thank you once more.
Thank you so much.
Jsem slepý a nevidím. Ještě nemám čo vidět. Okay, so as you see, the most authors are focused on the last presentation. And this is collaboration between Linz and Bratislava. So first three authors are from Bratislava, myself, Anna Kursarova and Adam Šeliga, who by chance has just today anniversary, congratulations. And from Linz, Susanne Saminger, Platz, and Eric Peter Clement. Of course, we have already heard about copulas here, but only about two-dimensional copulas. Recall that what are copulas, say verbally, they are the stochastic part of the random vectors. When we have some random vectors, so dimensions at least 2 to have vector, then we have marginal distribution functions which characterize it. But we have also stochastic dependence, and the stochastic dependence is just covered by copula. To have an immediate imagination, what can be this stochastic dependence? Think only on independence, because mostly we have met with independent random variables. And copulas are, in some sense, functions defined on these marginal distribution functions to obtain joint distribution function. So for independence case, of course, we have standard product, which plays the role of copula. But of course, there are several others. Now, if we think on this, that copula can be seen as a particular distribution function. So this is just distributional function which has marginal distributions uniformly distributed on the unit interval. So each copula is in fact also very particular dependence function, and then distortion by means of this marginal random marginal distributions, we obtain the distribution of this vector. But of course, I will not speak about this. I will speak about very particular class of such copulas, which in some sense is having in mind some computational aspects, the simplest properties, and this in the framework of functions are just polynomials. Because they appear everywhere, and we can do, for example, when thinking on analytical approaches, having in mind derivatives and so any derivative exists there, and so we can play with them. But if I will ask you, okay, and you know some polynomial copula, of course that immediate answer will be product, but some other. So, okay, I will present some of them. So, recall that when we want to have a functional description of a copula, this was done by Radek here. You have recalled two-dimensional copulas, okay. But in the general case, when we have dimension d is integer greater or equal than 2, then this is function which can be seen as the reaggregation function with 0 as annihilator or 0 element, and 1 is neutral element. But of course, sometimes there is problem. What does it mean, neutral element? If we have fixed function with given dimension, DRE function, so neutral element means if all inputs up to 1 are equal to 1, then the output is just this element which is remaining. And of course, this has statistical interpretation and so on. This can be seen immediately why it should be like this. But okay, functional approach is this one. Okay. And we are now just in the point where it has stopped by several other colleagues. Okay, so I want to speak about polynomial copulas, D copulas. So this means simply they are polynomials of D variables. But of course, we have some constraints, boundary conditions, for example. And in the case, sorry, maybe I have forgotten something to mention here, functional approach. Yeah, I have forgotten to mention that very important and not so easy to verify property is the increasing property. But formally, from functional point of view, if I will take some d-dimensional rectangle, we can play with mixed derivatives. And this d-increasing means that these mixed d differences are non-negative. Okay, so differences if I play with rectangles of corresponding dimension. And if we have polynomials as copulas, as I have already mentioned, all derivatives exist. And say this characteristic property of D copulas, D increasing property, can be somehow simplified from D differences into mixed D derivatives. So fixed D derivative should be non-negative. And for polynomial case, of course, this is standard density. So our copula can be represented in this form. C as density, we see this also somewhere here, that it's non-negative. And in general, it can be seen as this mixed derivative of our copula. This derivative should exist up to points of measure 0. But in such case, for integration, it doesn't change anything if we add there any value. So usually convention puts 0 if this derivative does not exist. But this is not the case of polynomials, because when we are there, all derivatives exist. So we need not have this convention. But okay, we can play either directly with copulas or we can play with their densities. I here mostly focus only on these copulas. Okay, maybe one of say the most important result is here, and this can be seen as a necessary condition for polynomial copula, how it should look like. So this is form of any DRE polynomial copula. And what is here, we should somehow detect this. We take any two coordinates, so coordinates I and after some coordinate j. We take this 1 minus xi multiplied by 1 minus xj, and here is some arbitrary polynomial, for the moment arbitrary polynomial, and here is the product of this. Because what we want to somehow stress here is what is the form of such polynomial copula. So we are not claiming that this is a copula, but what is important, boundary conditions, 0 being 0 element, 1 being neutral element. This is equivalent with this form of arbitrary function when we speak about this polynomial function. This means this will be at the end that what we want to continue with quasi-copulas, with semi-copulas, they have the same boundary conditions. So they should have also this form. But they have another properties for quasi-copulas, one Lipschitz property, and for semi-copulas only monotonicity. And of course, these boundary conditions. So we already know how it should look like. And when we will think, okay, fine. So what is the simplest situation? Of course, the simplest situation for polynomials is if they are 0. So take all these polynomials Pij that they are 0. We obtain this product. So, of course, in some sense, the smallest dimension of a polynomial copula to be, let's say, polynomial, the smallest power is the power corresponding to standard product. And this means this is this d. So this is the smallest possible, say, degree of polynomial copulas for fixed dimension d. Okay, then say what is the next? Still very simple and say therefore trivial. So what is the simplest polynomial up to the 0? Also 2. Constant. Yeah, so real constant and different from 0. In our case, this means say at least one of these polynomial should be constant different from 0 and all others are 0. What will be the degree of this polynomial? Dimension d, take it as fixed. Yeah. So, of course, we see here that this has, once it is constant, degree 0, degree 1, degree 1. So this is degree 2 with this. So this is d plus 2. We have a very funny result. There is no polynomial copula which could be polynomial of degree d plus 1. So either it's d, but that means only product. And the next, say the simplest which exists are related to d plus 2. But of course, when I have told that, up to 1, which is constant, all others should be 0,
this is not that it should be. This was only as an example, because of course, any of them can be either zero or constant, but at least one of them should be non-zero. Then the corresponding degree of the polynomial is d plus 2. And by chance, people which work with copulas, they even know how such copulas are called. This is early Gamble, early Morgenstern family of copulas. It can, though mostly people know it only in binary form. And in binary form, when d is equal to 2, so then we have only one pair of I and j, only 1 and 2. Yeah. So in that case, we have that here will be some constant, and here will be 1 minus x multiplied by 1 minus y. In dimension 2, usually we don't use indices, but x and y. Yeah. And of course, still we are in the situation that it's a necessary condition, but what is sufficient that we will obtain a copula? So again, people working with copulas know that this Fermi-Gamble-Morgenstern family has this parameter, usually denoted by lambda, not by Bij or Aij. And this parameter should be between -1 and 1. This is easy in some sense to check because, as I have mentioned, the density should be non-negative. Density in this case is the second mixed derivative. So when we play with this a little bit, we obtain this immediately. Okay. So what I have already mentioned, that this product is, say, polynomial with the smallest degree, which can be copula, so, and no d plus 1 and d plus 2 are this early Gamble-Morgenstern. Here we have this example how it works. And as I have mentioned, usually in statistical literature, here is used lambda, usually. And of course, we can go to higher dimensions, but we will see this a little bit later. This was known in some sense. It was known. So degree 4 is clear. This is Gamble-Morgenstern. So then the next one is degree 5. Oh, but when you start to play with such problem, finally you obtain the result that it depends on 3 parameters. And there are 12 linear inequalities. We were not able somehow, our computer skill was not sufficient for this. Then Susanne has asked her colleagues from faculty which are working with computers and so, and it has taken quite nice portion of time. So then when we just now are trying to fight with ternary copulas of degree 6, we have seen that in the actual situation with hardware and software, it's impossible. But in some sense, it's clear that it is solvable only if we want to have a complete, full characterization. We should wait till in real time we will be able to obtain the result. But sorry, without computer, it's not possible to verify these things. So these characteristics for this degree 5 for binary copulas, I should tell, we have presented in dependence modeling journal. You see, it's already 5 years ago when it was appearing. And here we can see this form for degree 5. Yeah. And only to have some imagination how these triplets look, it's not difficult to see that these triplets are characterized by linear inequalities, but this means that the solution is a convex set. And this is the same set only from different points of view. Yeah, only to see that some things you can see that, for example, A and B you can exchange and still it stay copula. A and C or B and C you cannot exchange. this has another property, but this is A is related to X, B is related to Y, and C is related as to constant 1, what was proposed by Lutzka as a nice constant. Okay. Here only a small remark that, for example, if I will take survival copula, if we don't know, I will not give a formula for survival copula. I will only mention if copula C is describing stochastic dependence of random variables X and Y, capital X, capital Y. If I will take another vector, minus X minus Y, so its copula is just this, what is called survival copula. But we have also algebraic expression for this. So when we go here, this survival operation preserves the fact that from polynomial copula we obtain polynomial copula if it is of some degree. Also, the output will be of the same degree, so this should be of degree 5. Therefore, it should be characterized by some 3 real constants. And here we see this, say, link, how it is. And what is well known, of course, minus applied to minus, we are back. So survival of survival is original copula, but also here this involutivity is in some sense seen if you apply to this formula minus A minus B, A plus B plus C. The same story once more, minus minus A is A, minus minus B is B, and A plus B plus C, but there now we need plus minus A plus minus B, we are back by C. So ABC is obtained really back here. There is only one example, only to see how it works. Maybe I should check. Okay, the time is, as usual, by my lectures running very fastly. Now I stay still with dimension 2. Quite interesting result for construction of copulas we have obtained with Peter Clement and Maddalena Manzi. This was related to special types of copulas. And what is interesting for any copula, binary copula, this transform of this copula, C and here, x plus y minus cxy is standardly called dual copula. This has nothing to do with dual aggregation function. This is duality for one Lipschitz functions, and copulas are one Lipschitz functions. Yeah, I think here the result is that for arbitrary copula C, this DC is also copula. But what is easy to see in some sense is if C is polynomial of some degree n, then this is degree 1, this is the same degree n. So for sure, in this parenthesis is also polynomial of degree n. So this DC should be of degree 2n. And we obtain copula DC, but then we can recursively apply again. And we will obtain degree 4n and so on. Going here back, it's not difficult to see that up to some boundary points here, when I compare this with 1, this is smaller than 1. And therefore, in some sense, this construction leads to smaller copula. DC is smaller than C. So if I consecutively apply, I will obtain sequence which is converging to the smallest two-dimensional copula, which is Lukasiewicz T-norm, and here it is usually denoted by W as weakest. Okay. Maybe what is interesting to see, when we have seen this, immediately it has recalled to us quadratic construction of copulas, which we, with Anka and Gaspar Mayer, were preparing. So what does it mean, quadratic construction? This is one of examples of quadratic constructions. Imagine that if I denote C, X, Y by Z, So this is z times x plus y minus z. When thinking on polynomials, this is polynomial in 3 variables of which degree? Yes, as you have told, 2. This is quadratic function. And then we were, of course, interested, having some other polynomials, quadratic polynomials, when we apply it, x remains x, y remains y, and as z, we take c, this copula in point x1. It's nice two-parametric class and so on. I will not go to the details, but what is important that now we have construction method which leads to new copulas, and degree is the same. So you can have now a sequence of copulas, but with the fixed degree of polynomial which it represents. So, okay, I should take some other. Lubka is still here. Maybe what is quite interesting is a construction which was proposed by Nelson in exercises. Please try to prove that if I define for fixed constant AB from the unit square such function which is defined by means, this is volume of copula, I will not explain about, but then it is copula for arbitrary AB. What is interesting, you can immediately see that if original C is polynomial copula, then this is also polynomial copula of the same degree. So it preserves degree. And for example, survival copula is one of the special cases here. This is here hidden. This corresponds to constants A and B equal to 1. Another quite well-known construction method in two-dimensional situation is Darshov product, or sometimes called Markov product, because it's related to Markov kernels. Again, if we start with polynomial copulas, then also this Darshov product is a polynomial copula, only we are not sure with the degree, we have only upper boundary. It cannot exceed this n1 plus n2 minus 2 degrees, but it can be smaller. Yeah. And if we go to this early Gumbel-Morgenstern copulas, so if I say compose two such, then again we stay in the same class, only the corresponding parameters are multiplied and divided by 3. Next are some, say, things which are related to d greater than 2. Here I will only very briefly tell that if I take our coordinates and take some partition there, yeah, this is a representation of this partition. For each of these, I can define the corresponding copula, and the product of these copulas is again copula. And what is important if I think on polynomial copulas, so here I should sum up these exponents, these polynomials. But this is well known from if you multiply two polynomials and you have some degree here, some degree there, so the product is again polynomial of degree corresponding to the sum of the original degrees. Okay, so this is quite a nice construction method. For example, for ternary copulas, we have in this case only 5 partitions, and 2 of them are trivial. Of course, that if I take only singleton, then there is nothing new, no new information. Or if I take singletons as another trivial partition, I obtain just the product. So these are not interesting situations. But these are interesting because suddenly, if I take arbitrary two-dimensional copula, which is polynomial, then I will obtain again, ternary polynomial copula, and the degree, of course, will be +1. And these are up to permutations, say the same story. So formally, we have 3 classes of ternary copulas, which are of degree 6 polynomials. I think that it should be already enough of my speech. Maybe what we want now focus on are the Bernstein copulas, which are related to approximation of copulas by means of Bernstein polynomials. So this is something what I look personally forward to work on, this quite interesting thing. So thank you for your attention. So it seems so that I am the only unpolite president who has presented longer. Please, some questions, comments. So maybe the important question, when will be the dinner? Yeah. Okay, so thanks you once more, not only for myself, but also for all people which were presenting here, and have a nice evening.